Okay, this is the review for the study guide, so please copy this information into your study guides, and this is what you guys are going to be able to use on your test coming up. So we're just going to plow through them, and then we'll be able to discuss these also during our upcoming Zoom session. So draw a water molecule with partial positives and negatives and with hydrogen bonds between them and explain why it's polar. First of all, can you draw a water molecule H2O with two H's and one O? What you need to know is that the oxygen is the stronger in the tug of war, so it's going to gain the electrons in this electronegativity battle. So your oxygens are going to be delta negative and your hydrogens are going to be delta positive. So that's the first thing that you need to know is with the partial positives and the partial negatives and with hydrogen bonds between the water, that is the main concept, also the hydrogen bonds. This is not a hydrogen bond. This is a covalent bond. This is a covalent bond. These are covalent bonds. They exist within the water molecule. Hydrogen bonds exist between water molecules. Since this portion of the water molecule is partially negative, it will form this electrical attraction with the partial positive of the hydrogen of the other water molecule. Why is it polar? It's polar because it is bent. This bent nature creates the ability to have a partial negative and partial positive. Explain the net results that hydrogen bonding has on the properties of water in terms of surface tension, stickiness, shape, temperature, and what happens to bonds when changing from liquid to gas. So let's take a look at the hydrogen bonding. Again, it's this reaction that's taking place. If you remember, we did this drop experiment where we have the water and it's forming hydrogen bonds with each other. This hydrogen bonding sticks those water particles together. If you remember when we applied the soap to this, the soap broke the hydrogen bond, it broke this, and what happened is they're no longer sticking to each other and all of the water particles will then fall flat. And that's what happened to your drop as well. So in terms of surface tension, we also did another experiment where we had some hexane and we had some water. And the aluminum, if you remember, floated on the surface of the water. So here's the water here, and here is the aluminum. Why did it float? Well, it's because of the surface tension. These hydrogen bonds are sticking so strongly to each other, they don't want to allow the aluminum to pierce through it. If you apply a strong enough force, then the aluminum will be underneath the water, it will be underneath all that surface tension, and it will be able to sink because it is denser than the water itself. Okay. Temperature, what happens to bonds when changing from liquid to gas? Well, if you remember that it is these hydrogen bonds that keep water a liquid. So the hydrogen bonds keep water a liquid at room temperature. So what you have to do is you have to increase the temperature to break these bonds. In order to pull these apart and allow them to be going into the gaseous phase, they need to be separated from each other. So when you increase the temperature, it's going to break those bonds. Not the covalent bonds, but the hydrogen bonds. Increasing the temperature breaks those hydrogen bonds, and then this enables it to go from the liquid to the gas, and then those particles will then float away. What happens to the density? When you go from 100 to 4 to 0, you don't have to know the actual numbers from your lecture, but let's say we are decreasing in temperature. We're going from 100 to 4 to 0. At about 100, it's about 0.98. At about 4, it's 1.0. This is when it's actually the densest. This is what happens to most materials. As you decrease the temperature, they lose their energy and they become closer to each other. That's what happens with water as well. But then water has that unique property to where it's going to increase its density. Decrease the density as it's about to freeze. It increases the space before it occupies its crystal structure, and then it will become ice. What happens to the density? It gets less dense as it approaches 4 degrees Celsius, but then the density begins to decrease as it occupies more space. So the crystalline pattern compared to normal water in terms of its density, if we're drawing water particles as just single items like this, one water has the ability to form hydrogen bonds with 4 others, and it forms this structure right here. However, when you're going to the solid form and the crystalline form, this is the liquid, when going into the crystalline form, it forms the honeycomb hexagons with lots of space in the middle. This is the solid phase. If you look at the formula for density, density is equal to mass over volume. We've increased the space, therefore we've increased the volume. Volume and density are inversely related, so if you increase the denominator, you're going to decrease your value. Understand the difference between solutes and solvents. Okay, solvents are the things that do the dissolving. Remember, water is the universal solvent. So these guys do the dissolving. The solutes are the things that are being dissolved, like salt. And again, we have aqueous solutions. Aqueous solutions, the root word of aqueous is aqua. These are water-based. Polar solvents dissolve which 2 types of molecules? Well, if you remember, water is polar because it's bent. So think of polar being an example of water. Polar solvents, water is a polar solvents, dissolve which type of molecules? These dissolve either things that are polar, because if you remember, like dissolves like lab. They also dissolve ionic things, like sodium chloride. Okay, so ionic is an example of, if you remember, extreme polar, because the tug of war is so strong that the electrons have been pulled away from one has gained, one has lost. So it's an extreme form of polar. Okay, so again, water has the ability to dissolve those 2 different types of things. Things that are polar, such as hydrochloric acid. Okay, hydrochloric acid has a partial positive and a partial negative, meaning that this molecule is polar and there's a tug of war between the electrons. And extreme polar would be an example of ionic, would be something like sodium chloride. Why do these dissolve in water? Well, if you remember, water has its own partial positives and its own partial negatives. And the water that's the negative portion will line up with the delta positives of this molecule. The delta positives will line up with this delta negative. And it's the same thing for this. This will form those solvation spheres where the water completely surrounds each of those ions. Since they're able to completely surround these things and react with them, they're going to dissolve. But if you have something that is non-polar, like iodine is non-polar. Okay, this will not react with the water because water has these charges. Iodine doesn't have those charges. Like dissolves like. So we need another nonpolar substance to dissolve the iodine. What it means to be soluble. Soluble means that it is dissolvable, so it dissolves. Insoluble is something that doesn't dissolve. So in water, salt, which is ionic, will dissolve. It is soluble. Hydrochloric acid will also dissolve in water. It's polar. It dissolves. It is soluble. Iodine is nonpolar, does not dissolve. Therefore, if you drop iodine in water, it is insoluble. Know the effects of heating, cooling, increasing, decreasing concentrations has on solubility, and this is the solubility of solids. So let's make that clear right now. We're talking about the solubility of solids. Okay, if you have a graph, the graph would look like this. Okay, for solids, here is the solubility, and here is the temperature. When you increase the temperature, you increase the solubility, meaning that hotter things have the ability to dissolve things easier than cooler things. For example, when making my kids either chocolate milk or hot chocolate, okay, the hot milk dissolves it a lot faster, but more will go in, versus cold milk, if I'm dumping in a bunch of hot chocolate powder, it might not all dissolve, and it will take a long time to dissolve as well. So when you heat things, you increase the solubility, okay? And vice versa. If you decrease the temperature, you're going to decrease that solubility. Know the concept of like dissolves like to determine which substances will dissolve others. Well, going back to this, water is polar, and it dissolves things that are either polar or ionic. So if you're polar, again, you dissolve either polar or ionic things. And if the things dissolve and mix with it, it is therefore going to be loving the water, so it's going to be called hydrophilic. So you need nonpolar materials to dissolve nonpolar materials. Okay, the iodine will dissolve in something that's nonpolar because it itself is nonpolar. It will dissolve in oil. Oil doesn't mix with water, and so therefore this would be hydrophobic. So iodine would be hydrophobic. It does not like water. It fears water. Okay, going on to the next page. Know what electrolytes are. Okay, electrolytes conduct electricity. If you remember, we used the beepers as well as the lights to show that electricity was being conducted. So electrolytes, just like in your body needs electrolytes so that your nerves can have those electrical impulses. So electrolytes conduct electricity. What compounds usually become electrolytes? Well, you have to conduct electricity and you need ions. So electrolytes are going to be your ions or ionic compounds. And that's because they produce these positive and negative charges. What are non-electrolytes? Non-electrolytes don't conduct electricity. An example that we did in class is going to be sugar. While there is sugar in Gatorade, and Gatorade is considered to be electrolyte, it's not the sugar that makes the Gatorade the electrolyte, it's the salt. It's the ionic compounds that make it an electrolyte. Sugar is covalent. And when it goes into the water, it can't get ripped apart. It can't produce ions, so it doesn't conduct electricity. Lights went off. Okay, lights are on. Difference between hydrates and anhydrous substances. So we use this substance called copper sulfate pentahydrate. It's a hydrate that has water in the crystal structure. Water was locked in that beautiful blue crystal. Water locked in the crystal structure. And then last semester what we did is we heated that hydrate and it released all the water, it evaporated, and we were left with this dull gray powder. That was the anhydrous. The anhydrous lacks the water. So you have the copper sulfate pentahydrate, which has the water, then we just have the normal copper sulfate, which lacks the water. And if you remember, we took this stuff and we rehydrated it by putting water back in, and we produced the hydrate. Why solids dissolve more quickly when stirring? This was the solubility races. When you increase the speed, you're going to increase the collisions. Of the water particles with the crystal. So if you stir faster, you're increasing the speed, you increase the collisions. When it's warmer, you're increasing the speed of the particles, more kinetic energy, you increase the collisions. But smaller, the size is a different factor. Remember, we had the rock salt, which was very large, and we had these smaller crystals. If you can imagine cutting this giant crystal into smaller crystals, and if you count the number of surfaces, 1, 2, 3, 4, 5, 6, 7, 8 versus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. What's happening here is we're increasing the surface. What does that have on the effect of dissolving? Well, the dissolving actually takes place on the surface. So the more surface that you have, the easier it is to dissolve. So on your test, there are going to be 3 types of mathematical problems. One of them is going to be a molarity problem, one of them is going to be a percent problem, and one of them is going to be this, with calculating the amount of precipitate that you have or calculating the amount that can still be added to your solution. Okay, so if you can create an XY axis, and let's say this is temperature over here, this is solubility over here. Let's go ahead and create some numbers. Let's go 0, 5, 10, and 15, and 10, 20, and then 30. Okay, we're going to create some points. It's going to go like this. Then there's going to be a couple of questions. Know the solubility chart, what it means to be saturated. Saturated means that it is full. It is maxed out. It cannot hold any more. So this is the solubility. At 5 degrees, it can hold 10 grams. When we increase the temperature, we're increasing the solubility. So at 10, it can hold 20 grams. At 15, it can hold 30 grams. Okay, so let's say that at 5 degrees Celsius, so at 5 degrees Celsius, let's say you have 20 grams. what does it mean that you have 20 grams at this point right here? Okay, so at 20 grams right here, first of all, is it dissolved or is it not dissolved? The solubility is at 5 degrees is 10 grams. We have 20 grams. We're actually above what the maximum can be held at that temperature. So it's going to form a precipitate. Everything that is going to be below this line and on the line is going to be dissolved. So this is all dissolved in this whole section here. Everything above it's going to be a precipitate. So here's the max. Here is the saturation. This is the maximum it can hold. So yes, it's still dissolved even if it's maxed out. Anything above maximum will give you a precipitate. So the question is, how many grams of precipitate will I have? Well, you just take, we're at 20, it can only hold 10. So if you do the mathematics, there's going to be 20 minus 10. So from here to here, we have 20 minus 10. 20 minus 10 will give you 10 grams of precipitate. Let's take a look at another question. What temperature would this have to be in order for it to be dissolved? So we're not going to change the amount, but we can change the temperature. And remember, if you heat things, we did a lab where we heated a crystal, and we found out what's the temperature that it's going to dissolve. So if you heat it and increase the temperature right here, we went from this temperature to this temperature. So we're heating it, we increase the temperature, keeping the same amount. What temperature is that going to be? It's going to be 10 grams, or 10 degrees. Okay, let's say I continued heating it to 15 degrees. Okay, am I dissolved or precipitate? I am now dissolved. At 15 degrees, here's the question, how much more can be added to your solution before precipitate forms? Here's the maximum it can hold. I now have everything dissolved. I can add everything up to here. So if I take my 30 minus 20, I can actually add 10 more grams if I'm at 15 degrees Celsius. So when you're above the line, you're precipitate. When you're below, you're dissolved. If you're above, do the difference of those. That will tell you how much precipitate is formed. If you're below, that tells you how much that you can add. Know the units of solubility. The units of solubility are grams per 100 milliliters. Very similar to concentration. Your grams is the amount. And this is going to be the amount that's in the solution. That's the amount, that's the volume of your solution. Know the difference between solubility of solids and gases at different temperatures. We took a look at the solubility of solids. Now let's take a look at the solubility of gases. So when you are increasing your temperature, what happens to the solubility? It's the exact opposite. When you increase the temperature, solubility is going to be low. Low temperatures, the solubility is going to be high. So it looks something like this. Okay.